Hello, welcome to our first lecture in Computational Fluid Dynamics. Our first chapter is mesh generation. First, I want to have a short look at the outlines. If you start a digital twin, a simulation, you have to look at the geometry. Then I want to explain you why do we need a grid? What is a numerical grid? I want to tell you something about element types, grid types, different grid designs and guidelines, and a little bit about the strategy, why we have to choose one grid for one problem and one grid for another problem. And I want to tell you something about solution adaptation. The solution of a simulation or a calculation always depends on the mesh you choose. Yeah, that's in every numerical simulation the case. So if you choose the right mesh for your right problem, you get good results. If you choose the wrong mesh for a problem, you will get wrong solutions. Okay, first we look at the geometry. What is a geometry? Yeah, what is a geometry? We're starting at the point of all problems is to think about geometry. Do we have an airplane, or do we have a ship, or do we have a car, or do we have the whole earth and make a weather forecast? Or for example, here we have our friend, the T-Rex, the dinosaur, and that's really complex problem. Or we can have simple problems like this box here. Yeah? Like you imagine you live in Minecraft, then everything is built with boxes. Yeah? Then you have a really simple geometry. Yeah? Why is this geometry simple? Because here our coordinate system can be done really easy. Here with this geometry, our coordinate system will be quite complicated. So, that's geometry. The geometry can be created if you want to do a numerical simulation. If you want to do a CFD simulation, you have to create the geometry. And you can always build your geometry from top down or from bottom up. Yeah? What does this mean? From top down, yeah, it means you have your computational domain, and you divide it more and more in primitive shapes, just like cylinders, bricks, or so. Or if you do it bottom up, yeah, then you think about the edges and every point of the dinosaur, and then you construct every point after each other. Doing this is quite advanced. It takes most of the time of your simulation job, and there can happen a lot of mistakes. Yeah? If you do the wrong mesh, if you do a bad mesh, you will get problems. You can never solve your numerical simulation if you have bad meshes. Yeah? And you need help to build up a geometry. You can do it with CAD programs. You maybe know CATIA, or you can do it with a design modeler from the ANSYS Workbench. SpaceClaim is a good program, or there are many other CAD programs like Inventor, or for example AutoCAD. And with all these programs, you can build up your geometry, and then you need a mesher, and then you can do your mesh. So there are many different strategies to do it. Okay, there are three main steps in computational fluid dynamics. Yeah, you first start with a preprocessor. Preprocessing means you prepare your simulation. You start doing it. Then comes the solution process. The solution process, if you prepared everything well, if you solved your equations well, more or less the computer will do the solution process for you, but the computer needs a lot of time, and the computer will need a lot of memory. Yes? So CPUs, and normally you use a lot of CPUs, yeah, with these problems. I know companies that have computers that use over 7,000 CPUs for one simulation. And in CFD, it's also really easy and simple to spread the simulation over the whole memory, if you have a shared memory system, or over the or many CPUs. Yeah? And if the solution is done, more or less, yeah, if it runs well, you just have to wait, you can drink a coffee, or you go home, sleep at night, you come back, and in the morning the solution process is finished. And then the post-processing step starts here. And post-processing means you create from your results pictures. Yeah? If you can imagine weather forecast, no one can imagine anything if you just see a lot of numbers. You have to see visualization of the clouds, of the streams, of the temperatures. Okay. And one thing is really important here. Do not process with CFD calculations unless you have a high quality mesh. That is really important. You can make really easy bad meshes, you can make it fast, but then your result will be wrong. Yeah? The simulation always depends on the mesh quality. Yeah? If you start with a bad mesh at the beginning, everything will be in bad quality, and also the results will be wrong. Okay, so first step of the solution process is our mesh generation, and that's like an art. That's there's not one way to make the perfect mesh. It depends really much on your numerical solvers, on your differential equations, on your problems, and on your boundary conditions, also temperature range, pressure range, velocity range, which mesh you have to use. Okay, and the mesh, we call it mesh or grid, or if you want to be more scientific, you call it discretization, or you can also call it control volumes. That's maybe the best word, control volumes. You separate your geometry. If you have, for example, a pipe, you separate it in different control volumes, and for every solution you have to solve your differential equations. So there is now a bit of an example. Yeah? It's one cell. I just show you one control volume, one cell, and I made it a bit easy. You can have different geometries, but the most easiest geometry here is a hexahedral cell. Yeah? Hexahedral cells, yeah? A block like in Minecraft. That's easy to build up a differential equation system. Yeah? You have here 90-degree angles, which makes it easy. If you don't have 90 degree, you need a kind of Jacobi matrix. But if you make it 90 degree, you can just look at the bottom, and you can place your ruler here, and you can say, okay, my delta x, yeah, is here, for example, 5 centimeters. And the same with the height, delta z, it's easy to measure, or delta y. And we often need, if we want to solve now this, for example, fluid flow or electrodynamic field over this block here, you will always need areas. And to calculate the area of this control volume at the side here is rather easy. You just multiply delta x with delta z, you have this face here, or you can multiply delta y with delta z to get this face, or you can multiply delta x with delta y and get the area here at the top. And how big is the volume of this block? I think you should all know this from your mathematics classes. V is defined by dx times dy times dz. So if you want to fill this block with water, you can just calculate the volume, and if you know something about physics, the y and so on. Okay, and important is you can have 2D problems. In former times, when the computers were a bit slower, we had a lot of 2D, two-dimensional problems. Nowadays, I would say most of the problems will be solved in 3 dimensions. Okay, so important point here, yeah, creating a good grid. Time spent in generating a good grid is always time spent well. If you do a good grid with good quality, you will have an easy run, you will have no problems, you have no problems in visualization, in numerical solution. But if you don't do a good mesh, then problems will come later. Okay, now let's look a bit what we deal with computational fluid dynamics. You can also have blocks and meshes if you do finite element methods for strength of force calculations of solids, or you can use for electric fields and for a lot of different physical problems. But in computational fluid dynamics, more or less, we are interested in fluid flow. And the most important question is how much mass will be spent on one side and how much mass will come outside here at the exit of this block. That's most important. And it should always be conservative. What means conservative? If you have here a mass flow of 5 kilograms of water from this side, it should be the same at the exit. Yeah, we will never lose mass. Yeah? Okay, so how can we calculate it? Let's get a bit deep. Let's go a bit more in details. Do a little deep dive. Yeah, we have here our mass flow and our phase. You learned it before. The phase of the cell is dy times dz. You multiply it with rho, the density, and the velocity of the water that comes inside here, and you get a mass flow. And on the other side, what comes out of the cell? What is the mass flow that flows outside? It's nearly the same. You have rho, the density, times my velocity at this phase, and you multiply it with the surface of this phase, yeah, dy times dz. But here is an additional term. And what does it mean? This term includes a flow that goes to the side, it comes outside of the walls. Because if you fill in water here and you have no walls and the water can flow out of the cell at the sides, you can get some flow to the sides. Yeah, it can come out of this phase. Okay, so we will come back to this point later. Get more complicated. Yeah. Okay. So now, before we now want to step into differential equations and in mass conservation or momentum conservation, let's go step back. Yeah, don't make it too complicated. Let's look how does the grid influence the solution. I told you, normally it looks like a block, the mesh, but if it does not look like a block, it will influence your solution. Okay, so the cells, what is good? It is, for example, good if mass flows into a block if it goes in a 90-degree angle. Yeah, as the phase is a bit shifted, yeah, or there is another angle between the inflow and the phase, you will not get this good quality of the solution. Yeah, But there are other things. Maybe you don't have so much money, maybe you don't have so good computer. CPU times are important. Can you solve the mesh? Can you solve the solution? Beginners always make the same mistake. They build big meshes with million and cells. They spend many days building a big mesh, and afterwards they realize, oh, my computer is too cheap. I can never solve this problem. And then they start goes. They have to step back. They have to do a more coarse mesh, and they lose quality. And another important, what are the quality aspects of the mesh? For example, the grid density is important. How many cells do we have in a special region? Or the length to volume ratio is important. We have really long cells, really thin cells. This will not be a good numerical solution. You have to spend more resolution on this long thin cells. Also, skewness is a problem. Do we have very sharp angles? Do we have 90-degree angles? Are always the best. But if you have really sharp angles, quality will be not so good. Which type of cells do we have? We have tetraeders, hexaeders. We already seen hexaeder meshes, and I will explain a lot of things with hexaeder meshes. But tetraeders will be also sometimes a good solution, maybe a fast solution for beginners. And what is also important? Boundary layers. If we have somewhere a boundary, a wall, or an exit, or if we have a car and a complicated geometry or an airplane or so, we have to make a better resolution in this area, finer resolution. So, and there's another problem. I want to mention, you never know where does the fluid exit. As the fluid comes from this side and it exits, all the mass flow will go through this block and will come outside here. It's a really simple simulation. I can tell you, if I have a mass flow of 5 kilograms from this side and 5 kilograms and can only exit here, it's easy. Everyone can tell you 5 kilograms per second will come outside of this side. But what happens if there are other faces open for the fluid? How much of the fluid will go into this direction and how much of the fluid will exit here? Or if the fluid enters here, how much will exit from here? And it gets even worse. There will also come fluid from the other cells into this cell. So you see, if you have this hexaeder mesh cell, you have about 6 different phases from where fluid can come into your region or can exit the region. And how can we solve this problem? It's easy. We just calculate all the possibilities. So you can imagine, if you have one cell, you need for every phase other differential equations. And not only for mass flow, you will also need it for momentum or turbulence quantity or temperature. So you will get a huge amount of differential equations, much more than cells. So that's why you need so much CPU power and so much memory of your computer. And we speak of maybe 20, 30, 40, 50 gigabytes of memory. Okay, but why do we have to solve, or which equation do we solve in general? And in general, we solve momentum, velocities, we solve, for example, temperatures or enthalpies, we solve masses, mass balance, we solve pressures, we calculate the pressures based on the mass flows, and yeah, more or less that's the most important. So the formulation of your system, the formulation of your problem in general will be always the same. Yeah? We will always have a variable and we have a derivation into every direction. For example, if it's a hexahedral mesh, yeah, a normal coordinate system, we will have your one general variable, which could be velocity or mass or temperature, and we make the derivation into the x direction, we make the derivation into the y direction, and we make the derivation into the z direction. And if we do solve all these problems, we call this the gradient. Grade phi, you will often see this, it's easy to write it, but it means a lot. If you write gradient phi, it means derivation in every direction of the mesh. And in computational fluid dynamics, there's a famous symbol called the nabla operator. And nabla looks a bit like a rotated, like vice versa, delta. Yeah? You know delta, everyone knows what delta is, but delta is a difference between two positions. Yeah? And the nabla is just turned around, the symbol. And nabla is a maybe you have not heard about it. Yeah? Where does it come from? Nabla is a really old symbol in mathematics. It's, I think, even older than the delta symbol that came from the Greeks. And the first observation of a nabla was done on this, on a over 4,500 year old picture from the standard city of Ur. It's today it's near Baghdad in the Iraq, and they had a high culture. They made a lot of arts and a lot of pictures, and there is one picture where they made a picture of a music instrument. Yeah, it looks like this. It looks like harp, and it gave the name to our mathematical symbol nabla, the nabla operator. So you will see this symbol more often now in the next time. So let's have a look. I told you a bit about hexahedral meshes, and more or less hexahedral meshes are a bit easy. Yeah, you have like a checkerboard. Yeah, you have your lines. Every cell has a neighbor here at each side, and it's a bit like a coordinate system. Yeah, if you have your coordinate system x, y, and you have your mesh inside the coordinate system, you can easily calculate every coordinate if you know the deltas between the mesh points. That's a structured mesh. And simulation codes or Cfd codes that run on structured meshes are really much stable, really conservative, mass conservative, momentum conservative. You won't have so much problems solving such a mesh, and it makes it much more easy to solve it numerically if you have angles near to 90 degrees. But sometimes, why can't we all live in such a world where we can use this checkerboards? Because we're not all in Minecraft. Yeah? Everything will look like these blocks in Minecraft, and so we need other mesh types. We can have, for example, cylindrical coordinate meshes. Cylindrical coordinate meshes are not so common anymore. Yeah? In former times, maybe 20-30 years ago, we had a lot of Cartesian meshes, yeah, to fit, and everything looked like in Minecraft, and we had a lot of cylindrical meshes. Why did we use so much cylindrical coordinate systems in the past? Has anyone an idea? I can tell you, because many fluid flow problems have something to do with pipe flow. And if you want to make a model for a pipe, for a pipeline or for water pipe, then it's really good if you take a cylindrical coordinate system, because we can describe the mathematics really easy here inside a pipe if we use this cylindrical meshes. It will be really tough work to make a numerical model of a pipe, a round pipe, with a blocking, with a hexagonal blocking. On the other side, it will be tough work to make a model of a car in a cylindrical coordinate system. So that's not so common anymore nowadays. Nowadays we have more computer power, we can make advanced mesh types. So let's summarize a bit. Let's summarize a bit about the naming conventions of the meshes. I taught about structured meshes, meshes flowing in like a coordinate system in I, J, K convention. We can have unstructured meshes. Unstructured meshes is a really big field. I will show you in the next slides something about unstructured meshes, but you can imagine doing a mathematical calculation in a structured mesh, calculating a delta. It's really easy. Everyone can write this code, but writing a code for unstructured mesh, you will need much more mathematics. You need Jacobi matrices, a lot of this stuff, a numerical simulation of the geometry even. We can have so-called multiblock meshes. Multiblock meshes are also a really good feature. I use it really often, but it's mathematically difficult, and it is also for the computers, it means a lot of net traffic. You will have your solution of the differential equation in one mesh, and then you have to copy all the information to another mesh type, and then you make the next simulation there. Okay, in this field, multi-CPUs PCs help a bit, but you have a lot of net traffic. Or you can have another thing, so-called moving meshes. I don't want to go too much into detail if we have a look at these moving meshes, but there are problems where you really need it. For example, imagine you want to calculate the combustion in a gasoline cylinder or in a diesel engine, and you have your, for example, one question: which coordinate system is really clever if you have a cylinder of a car? For example, cylindrical coordinates, because you can really easily make the coordinate system for this pipe. But what is difficult? Opening and closing of the piston. This is rather tough. Then do you want to make the flow simulation for high crank angle numbers, low crank angle numbers, for big volumes, for small volumes? Every result will be wrong. So you need a moving mesh, a moving cylinder simulation.